Hello everyone, welcome to our discussion of section 4.7 where we'll be talking about antiderivatives. So up to now we've been talking about derivatives, as you know. Antiderivatives would be going back. So far we've had the original function and we were able to use several techniques that we talked about to obtain the derivative of the first derivative, second derivative of those original functions. So in some cases, we are given the derivative or the slope function for an original function, and we'd like to go back and obtain those original functions. So you'll see that the techniques are either easy to apply or easy to memorize. So for example, I'll just do an example right now, as you can see, and then I'll show you some the specific technique for obtaining the antiderivative of some derivative function. But before we do that, notice that, do you remember when we took the derivative of a function, if we had a constant value, such as 2x plus 5, the derivative of that 5 would be 0, right? So we would just get, for a function that was 2x plus 5, the derivative would just be 2. And we'd get 0 for that 5, the constant value. So when we obtain the antiderivative of a derivative or some function, for that constant, because the derivative of a constant is 0, we know that, we usually use the letter c as the constant value that may have been present in the original function f. So there may or may not have been a constant in the original function. For example, if you have y equals minus 3x or minus 3x plus 5, the derivative of both of those functions will just be minus 3. So if you're given just minus 3, then you don't know if there was a constant in the original function, and if there was a constant, what was its value? So we have ways of determining the value of the constant, and for that, we need to be provided more information. In addition to the derivative, we need to be provided more information so from which we can calculate the constant in the original function. Otherwise, if we don't have that extra information to calculate the constant value in the original function or in the antiderivative, we will just say use a capital letter for it, a C or D or some letter from the English alphabet. We'll go through some examples so you'll see exactly what I mean, but I just wanted to lay the ground for what is coming up. So for example, if we want to find the antiderivative of this, that means we want to find the original function, right, for this function, which is presumably the derivative of some original function. So you remember that when we take the derivative, we subtract the power, and then subtract this power, and then multiply the x. So if we were taking the derivative of this, suppose, we would say 2 times minus 3 minus 6x to power 1, and then the 5 would drop out. But we're not doing that. We're going the opposite. So instead of subtracting the 1 from the power, we add 1 to that power, and then divide this term, not the whole thing, this term, by the new power. The new power being the power after we add 1 to it. So let's just do it right now. So we have f being the original function, capital F, is equal to add 1 to that. So we get 3, positive 3, and then divide this term by positive 3. So we have minus 3 times x cubed divided by 3, which is the new power, plus, of course, that becomes 5x, right? Because the derivative of 5x is 5, so we know we must have had 5x, and then plus any constant that we may have had there, like that. You can name this constant anything, D, capital E, but usually in books and such, we just replace that with a C. So this is the antiderivative of that. In other words, this is the function from which that derivative came from. Okay, you can take the derivative of this and you'll get that. So 3 times minus 3 is minus 9, divided by 3 is minus 3, x2 power subtracted by 1, right? X squared, which is that, minus 3x squared, plus 5, and then of course any constant would have dropped out, right? Because we have nothing after that. So this is the antiderivative of that, basically. Now, if you know the derivative of if you have a derivative and you know the original function from which you could have come from, you can just write it down. You can just write it down from memory if you remember it correctly. If not, you can use simple techniques like this, which I've used right now. Just add to that power, divide this term by that new power, and then plus 5x. That would have been an easy antiderivative to get, right? Or you can memorize. If you can memorize some of these, I have listed there. I have listed a few of these for us to look at and actually use in the upcoming examples. So you can do that. And basically, if you remember, this one is the easiest, of course, the natural exponential function. It's its own antiderivative and derivative. These are, of course, easy, right? If you have a function cosine of x, the antiderivative of that would be sine of x, right? So if you take the derivative of sine of x, you get cosine of x. That's the idea, right? This is the original function from which this derivative came from. Even though I've titled this function, this is the antiderivative. So the derivative could, of course, be a function, right? Just like that. But the antiderivative, the function from which this derivative came from, or this function came from, are these, okay? And cosine of x, and of course this, because the derivative of cosine is minus sine of x, right? So if this is the antiderivative, then the derivative must have been, let me put a minus there. So minus, there is a minus here, okay? Because the derivative of cosine, we know it's minus sine of x, all right, from the past. And the derivative of sine of x is cosine of x. On this side, by the way, this table is not by any means inclusive of all the derivatives and antiderivatives we have. Your book, I believe the inside cover of your book, somewhere in your book, textbook, does have a very good list of all of the functions and their antiderivatives. So I would check that out. But these are some of the very useful ones. For example, if you have 1 over x, then the antiderivative of that would be natural log of x. If you had 1 over x minus 2, it would be natural log of x minus 2, absolute value of x minus 2. So this is a very useful one too. And this is the one that I just used. See, if you have a derivative like that, if this is a function that you know is a derivative and you want to find the antiderivative of this, you simply add 1 to it and then divide the term by the new power. Okay, that's exactly what we did here. We took this power, which was 2, add 1 to it, and divided this term by 3. X cubed divided by 3, the whole thing, right? And of course, this will be, we can simplify this. I just left it at that. But we can simplify this to f of x equals, let's see, can we, minus x, right? Minus x cubed plus 5x plus c, right? This is, we can simplify it to that if we want to. But I just left it at that because I just wanted to show you how easy it is to find the antiderivative of some function, which we know to be the derivative of some original function. Okay, and the derivative of this function, of course, is that. Okay, so here are some of the other useful ones. So if you have a function like that, that is a derivative of some, is a derivative, you want to find the antiderivative of this, you simply memorize this. Because we've seen this before, the derivative of tangent of x is secant squared x. Derivative of secant squared x, secant x, not secant squared, but secant x is secant x tangent x. The derivative of inverse sine of x is 1 over that, square root of 1 minus x squared, and so on and so forth, right? This is the hyperbolic sine, which has that derivative. So this is the antiderivative of that. And the antiderivative of the hyperbolic sine is hyperbolic cosine. Okay, so that's, I just included a small table here with some useful ones, but you can look up more of these in your textbook. Let's look at some examples then. Suppose we want to find the antiderivative of some of the given function. And we're going to do a bunch of these examples. Okay. And so here's one. Let's start easy, right? It's always a good idea to, when we learn something, to start out easy. So here is one. Like that. So we're going to use this rule of finding the antiderivative here. Just add 1 to the power, divide the term by the new power, okay, which is n plus 1. We're going to use that. Okay, so, all right, so I'll just call it for now, we call it with capital X, the antiderivative. So let's add 1 to that, we get 10, and then divide this term by 10. So we have 8x to the 10th power divided by 10, like that. And minus, add 1 to that, divide the term by the new power, minus 3x to the 7, divided by 7, right? That's pretty straightforward, isn't it? Nothing complicated about this. So plus 12x to the 4th divided by 4th. And of course, what should I add? So let's see what, so we should add the constant, right? The constant, the letter C. So plus the constant. Okay, we don't know. There could have been a constant. If this is the derivative of some function, then there may have been nothing there, or there may have been something there. But we account for it with just that plus C. Okay, and then let's simplify this, of course. What do we get? We get the antiderivative. We can certainly simplify this. We get 4x to the 10th power divided by 5, right? Minus 3x to the 7th divided by 7th, plus, of course, 3 times x to the 4th plus c. Okay, so this is the antiderivative. Using just this rule, that one. Okay. All right, so let's do another example. We call this one B. Suppose we want to find the antiderivative of cube root of x squared plus x times square root of x, right? So when we take when we find the antiderivative of things like this, I'm sure you remember that it's best to put the square root as an exponential, as a fractional power, right? So let's first do that. So f of x is equal to x to 2/3 power, and then plus, of course, this is x times, right? Remember from algebra, this is just x times x to 1/2 power. So we got 1/2 plus 1 is 3/2. So let's take it step by step, just to make sure that we don't end up making any errors. So that plus x to 3/2, right? 1, which is the power of x, plus 1/2, we get 3/2. Okay, so now it's easy to find the antiderivative, because all we have to do is add 1 to this and divide that term by the new power. So f of x, capital F of x, or the antiderivative, is equal to x to 2/3 plus 1 power divided by 2/3 plus 1 plus x to 3/2 power plus 1 divided by 3/2 plus 1 plus c, of course, right? The constant right there, very important. So we'll get to examples where, not this one, where we have additional information which allows us to calculate the value of this constant. We get to those too. I mean, I forgot to mention, but please pause the video. Once I write the example, before you see this solution, please pause the video. By now, you know that I am a big, in favor of, big supporter of watching the videos like that. Pause the video, then come back to it. Please do that. Okay, so then let's simplify this. We have the antiderivative equals 2/3 plus 1. Then we can get 5/3, right? That's 5/3. So let us write that. X to 5/3 power divided by the new power, right? 5/3 plus that one. So again, 5/2 this time. So plus x to 5/2 divided by the new power, which is 5/2, and of course plus the constant. So let's let's simplify these complex fractions, and we get as follows. We get 3/5 times x to 5/3 power plus 2/5 times x to 5/2 power, of course, plus c. Okay, so here's our antiderivative. Let's do another example. Suppose we want to find the antiderivative of this function. This time, let's pick a trigonometric one. R theta is equal to secant theta. You don't have to put these parentheses. I just put them there. It's a visual aid, and times tangent of theta. So it separates clearly the secant from the tangent function here. Minus 2e to theta power. Okay, so one thing that should catch your eye immediately is that tangent theta and secant theta. Tangent theta is a ratio of, so let me actually, so recall that secant of theta is the reciprocal of the cosine of theta, right? And tangent theta is the reciprocal, or not reciprocal, but it's the ratio of sine of theta divided by cosine of theta, right? This is important to remember because we can't have, when we find the original function, we need to qualify it with an appropriate domain, because in the domain we cannot have anything that is either pi over 2 or some factor of pi, or some interval that includes pi over 2, 3 pi over 2, 5 pi over 2. We cannot have any of those values or their negative equivalent, minus pi over 2, minus 3 pi over 2, and minus 5 pi over 2. We cannot have any of those in the domain of this original function, because it would make this derivative undefined. And even once we find the original function, it will probably restrict, it would probably have one function at least that has a cosine. As a matter of fact, it does have. So we're going to end up, let me bring this back before we discuss this further, because the original function this is going to affect the original function too. See, if we bring this back, we have secant times tangent, right? Oops, let me bring this into the view. We have secant times tangent. The domain of this function is minus infinity to infinity. So, but that's not a problem. This, however, is. So secant x times tangent x, that function has antiderivative secant x. That's what we have. So our antiderivative is going to be secant of theta. And secant of theta is the reciprocal of cosine of theta, which we cannot have any pi over 2 or any other angle that is a multiple of that in its domain, right? So, okay, so let's, therefore, knowing that the secant x tangent x, which is what I just showed you in that table, has antiderivative secant of x, then we can simply write, let's put capital R theta, right, equal secant of theta, and then that's really easy to find the antiderivative for, minus 2 times e to the theta, right? The natural exponential function is has an antiderivative which is equal to itself. And of course, plus the constant value, c. Okay? So now, this one, so this whole thing, let me, like that. And then, so then we say that on the interval, so this is the antiderivative on the interval that excludes n pi minus pi over 2 and n pi plus pi over 2. This is what I was saying earlier, that we got to remember this because we got to be careful about the domain of the antiderivative function. So this explains what the domain of the antiderivative should be. So this antiderivative does not exist everywhere. It exists only within this interval that excludes these quantities and these quantities. And of course, n is any integer, right? So n is an integer, like that. Okay? Like that. All right, so let's do another example. Suppose we want to find the antiderivative of this function, right? This is sine of t and the two times hyperbolic sine of t. And so let me bring that table again. So the hyperbolic sine, the hyperbolic sine has antiderivative hyperbolic cosine, right? Let me bring this table down so you can see the headings. This is what we have in our function. The antiderivative of that term will be hyperbolic cosine. For hyperbolic sine, the antiderivative is hyperbolic cosine. Okay, remember that. So as a matter of fact, let me write that. So recall that, let's start with this one. Sine of t has, I'm only doing this because this is the introduction section. I won't be doing that like that in the future sections, but we're just introducing this. So that sine function, sine of t, has antiderivative cosine of minus cosine of t, right? Because the derivative of cosine is minus sine of t, but this is positive, so we must have had minus in front of in the derivative, we must have had a minus in front of the cosine. So after this becomes minus sine of t in the derivative, the minus and minus multiply each other and we get positive. Has antiderivative that, and also that the hyperbolic sine has antiderivative hyperbolic cosine, sorry. So like that. Okay, knowing that, we can easily find the antiderivative. So that is going to be minus cosine of t plus 2 times hyperbolic cosine of t. Plus, of course, do you remember? C, right? The constant value that may have been there. Like that. Okay, so let's do more examples here. I'll do one just underneath this. I think I have enough space for that. So have E sine of x. All right, so first let's write this term with rational exponents. So we have f of x equals 2 times x to 1/2 power plus 6 cosine of x. And now we can easily find the antiderivative. So add 1 to this power and divide this term by the new power. So we have 2 times, right? 2 times x to 3/2 power, 1 plus 1/2 is 3/2, divided by 3/2, right? And then I'll simplify it after that. And then, of course, the antiderivative of this would be plus 6 sine of x, right? The derivative of sine of x is cosine of x, and the coefficient stays the way it was. Of course, plus any constant we may have had, right there. So let's simplify this. We have the antiderivative equal, flip this, we get 2 over 3 times 2, we get 4 over 3, and then 4/3 times x to 3/2 power plus 6 times sine of x plus c. Okay, pretty straightforward antiderivative. Okay, like that. Let's do another example. So that one was part E. So this is going to be f, let's say, and we have f of x equals, let's say, 2 plus x squared divided by 1 plus x squared. Okay, so let me bring that table back. How do we find the antiderivative of that? Let's see if in what I had in the table, if we have something that could help us, right? So here we have something that kind of looks like what, I mean, at least part of this, or this looks like part of this, right? See, the denominator is 1 plus x squared here, and the denominator here is also 1 plus x squared. So there is definitely a resemblance here, and that's our function, but our function obviously is more than this, 1 over that. If we had that, we'd be lucky because the antiderivative would be inverse tangent function. Really easy, right? But let's see if we can rewrite this so it looks like that. So this is a little bit, creativity here goes a long way. So let's be a little bit creative, right? So let's break this up, this 2, into 1 and 1. So we have 1 plus 1 plus x squared divided by 1 plus x squared, right? And then let's break this up again. You know, all through the algebra, we always said take the common denominator, right? That's what we always did. But now we want to go the other way around. We want to, instead of having a common denominator and all of that, we want to separate these terms such that we get a term that looks like this. Because if we have something like this, then the antiderivative is just inverse tangent. Okay? So that's basically the thinking behind what I'm doing here. So now let's separate this into 1 over 1 plus x squared plus 1 plus x squared, what you see in the parentheses, divided by 1 plus x squared. Okay? Now, look at this. We can simplify. This will become 1. This is just 1, right? So, we have f of x equals 1 over 1 plus x squared plus 1, right? And then now this piece has an antiderivative that we like because it's in our table right there. If that's the function you have, the antiderivative is that. So we know that one is inverse tangent of x. So this will be inverse tangent of x for that piece. What about this one? What term has a derivative equal to 1? X, right? Plus x. Can I end it there? What do you think? Can I end it there? I can't, right? I need to add something else to it. What would that be? The constant term, right? The one piece that we don't know what it is yet, okay? All right. So that should be that. And then let's do another example. this example is going to be a little bit different. So in this example, we want to find f in each of the following cases. So we have A. This is the f double prime, right? So what is that? That's the second derivative we have. Double prime of x equals x to the 6th minus 4, x to the 4th, plus x plus 1. That's an easy function to find derivative for, but we have to do it twice, right? First, we have to find the first derivative, and then from the first derivative, we have to find the antiderivative. Okay, so let's do that. So we have f prime of x. Since that's what they give us, I'm just going to go from. So f prime would be the antiderivative of f double prime, and then f would be the antiderivative of f prime. So add 1 to that, divide this term by the new power. So we have x to the 7th divided by 7 minus x to the 5th divided by 4/5, right? So let me minus 4 times x to the 5th divided by 5. How about this? Well, add 1 to the power of this, x squared divided by the new power. So we have x squared over 2 plus x, right? And then plus the c, the constant. So that's the first derivative, but we still haven't answered the question they're asking us, so we need to continue this one more time like that. So add 1 to that, we get 8. Divide that by this, we get 56, right? So we get 8x to the 8th divided by 56 minus 6 divided by 6. That would be 30 minus 4 divided by 30. Simplify that to minus 2 over 15, right? X to the 6th power, right? This is after simplification, right? I hope you can follow that. Increase this by 1, you get x to the 6th. Divided by this, you get 30. Then minus 4 times x to the 6th divided by 30. Minus 4 over 30 simplifies to minus 2 over 15. Okay, so how about this? Again, very simple. Add 1 to that. Divide this by the new power, which is 3. So 3 times 2 is 6. So x cubed divided by 6. And plus, of course, x squared over 2 plus, what about here then? So far it's good and nice, but what about c? What would we do with c? Well, if there was a c in the f prime, then we should have a cx, right? That constant multiplied by x plus another constant that may have been there, right? Let's call it d. Or you can call this C1, this is C2. However, which way you want to notate it is fine. But the main point is that you have to keep track of the constants, okay, as you find the antiderivative. Okay, so that's basically the final result for us, like that. Okay, let's do another example of this kind. This one is really simple, so I'm just going to fit it right underneath this. So suppose we want to find the antiderivative of this function, which is a double prime, f double prime. So this is the second derivative we have. Have f prime of x equals, so raise this by 1, so that'll be x squared, divide this term by 2, so you get 3. So we get 3x squared. Then cosine is the antiderivative of sine, but if you take the derivative of cosine of x, you get minus sine of x. So the fact that we have a plus sine x here, there must have been a minus already there, and then cosine of x. And then, of course, plus c, right? The constant. I'm pretty sure you guys are keeping track of what the c is, right? So suppose there was a 5 there, or something, or here, 5 or 10 or negative pi or something. Who knows? Some constant. After we find the derivative of this expression, we get nothing. For the constant, we get 0. It drops out. Nonetheless, we have to account for that using this constant or missing constant. We keep track of it by saying plus c. Okay? We don't know what it is, but we know it could have been there. Okay? And then, of course, let's find the antiderivative of this. We have add 1 to that, divide this by the new power. We get, that would be x cubed over 3, which would cancel this. We get x cubed, right? Then cosine of x has the antiderivative sine of x. And so minus sine of x plus c. If there was a constant there, then we must have had a cx here, and you find the derivative of that, you get c, right? And then, of course, plus another constant that may have been there, which let's call it d. Okay, and that's the antiderivative of that. Okay. So let's do more example here. And that one was B, I think. Yeah, so this would be C. Suppose we have triple prime of t equals e to the t power plus t2 minus 4 power. Okay. So here's a solution. So one thing before we start finding the antiderivatives, and we have to do this 3 times, right, to get the original function. Once for getting to the f double prime, once to get to f prime, and then once to get the original function. Let's note that this, because of this term, the domain of this function cannot include 0, right? Let's write that out. Note because of the term t2 minus 4 power, or 1 over t3 to the 4, right? That's the same thing. Then f triple prime t, right? That one that we are given has this domain. Negative infinity to 0, union 0 to infinity, right? It cannot include 0. So then as we find the antiderivative of this, we have to split this antiderivative for what works in each interval, okay? Because we have to account for that 0 as we find each antiderivative. So let's do that. So then we have for f double prime, and let me bring this down so you can see it. For f double prime, that's easy, right? It's simply e to the t, but I'm going to split this, and you'll see why in a second. So let's split it. E to the t minus 1/3, right? We add 1 to this. It'll be minus 3. Divide this, it will be minus 1/3. So minus 1/3 times t to -3 plus c, of course. I'm going to stop writing the c in red. So I just did it a few minutes ago just to make sure that you're paying attention to that part of the antiderivative, because it's very important. But now I know that you expect it, so I'm not going to write it in red anymore. So then if t, in this case, let's say it's in this interval, less than 0. Okay, so that, and then of course e to the t, the same thing, minus 1/3 t to the -3 plus, well, let's call this c1, because I'm going to need this. I'm going to need another constant for the c2, and because they're in different intervals. So this is t greater than 0, and that's t less than 0. They can never be the same. It's not possible for them to be the same constant. So I just want to distinguish c1, c2. That's all. Okay. Then let's find the next antiderivative for this, which would be f prime t. Then it would be, again, for the first term, it would be e to the t, and then plus, so add 1 to this, you get -2. Divide this by -2, you get positive 1/6. So 1 times t to -2 and plus. We used up c1 and c2. Let's use, well, we actually need those. We keep those, but then we add d1, d2. Let's do it that way. And then c1x, right, plus d1 if t is in this interval, and then e to the t plus 1/6 t to the -2 power plus c2. Sorry, I need to put a t here. Let me correct that with my thick marker here. That our variable here is t, so it should be t. And then c2t also plus d2. And then if t is greater than 0, then I think that's correct. So yeah. So then the next one, antiderivative, which would be f t is equal to e to the t minus, now add 1 to that, we get -1, and then -1, this term divided by -1 will be -1/6. So -1/6 times t to -1 power plus c1/2 c1 t squared plus d1, right? I'm just building on this. d1t plus e1. Of course, this is if t is less than 0, right? And then the same thing for this. For the other interval, -1/6 t plus 1/2 c2, right? Add 1 to this, divide this by 2, we get 1/2 c2 t squared plus d2t, right? d2t plus, let's call it e2, this constant, if t is greater than 0. Okay, so this is our antiderivative for that function. So because of the domain was split, we had to split the antiderivative there. All right, so let's do another example here. So suppose we want to find the antiderivative of 5x to the 4 minus 3x squared plus 4. And now this time they give us additional information. So we know that the original function at -2, this is the original function f, not f prime. F at -1, we know that it was equal to 2. Okay, we're going to use this information to find that c. That's the additional information I was telling you about earlier. If they want us to find c, the constant in the antiderivative, they need to give us more information, and now we have it. Okay, all right. So we have add 1 to the power, divide this by the new power, so we get x to the 5th power. Then add 1 to this, divide this by the new power, so we get minus x cubed plus 4x plus c, right? But so this is the antiderivative, and we know at -1 it was equal to 2. So let's find f at the antiderivative of -1. So -1 to the 5th minus -1 cubed plus 4 times -1 plus c, and this was equal to 2. Well, I should have put a 2. Well, I forgot to do it. Let me do it now. So this side is equal to 2, right? I should have started that with 2. I didn't. So, but it's okay. So -1 to 5th power is just -1. Minus -1 cubed is -1, minus 4 plus c, right? So we have 2 equals -1 plus 1, that's 0, minus 4 plus c. Therefore, c is equal to 6. Okay? So you can see everything on the screen now, like that. So now in here, we just replace c with 6. Now we know what it must have been. So the antiderivative f of x, or, well, let me call it f of x. Because this problem calls it f of f, so I'll call it that. F of x equals all of that plus 6. X to the 5th minus x cubed plus 4x plus 6. Like that. Okay. All right. Let's do another one of these. This one will be a trigonometric one. So f prime t is equal to 2 cosine of t plus secant squared t, and t between minus pi over 2 and pi over 2. And so that's obvious, right? We can't have t equaling pi over 2 or minus pi over 2 because this function will be undefined. The secant function would be undefined. And the additional information they give us this time is that f, the antiderivative f, at pi over 3 has value 4. Okay? So just remember that, let's recall that derivative of the cosine, no, I meant to say the derivative of sine. I should clean these pages before posting them on Canvas. I'll do that. Or that's sine. I should clean that up before posting. But the derivative of the sine of t is equal to the cosine of t. That's important. Why? Because of the first term. We want to find the antiderivative of this. It'll be sine of t. And also, the antiderivative of secant squared t will be tangent, right? So let's write that. So and ddt of tangent of t is equal to secant squared of t. And that's, of course, useful here, where we will find the antiderivative tangent t for that term. Okay, so recalling these two, then we have the antiderivative at t is equal to 2 sine of t, right, plus tangent of t for that one, plus, of course, the constant, right? Now, we know that this antiderivative at pi over 3 is equal to 4. So let's set that up. 4 equals 2 times sine of pi over 3 plus tangent of pi over 3 plus c, which this, of course, is going to help us find c. Okay, so we have, what do we have? We have 4 sine of pi over 3 is square root of 3 over 2. We remember that from basic trigonometry, like that. And plus tangent of pi over 3 would be square root of 3 tangent, so that would be square root of 3 over 2. So that would be sine pi over 3. So let me actually write it out. So this would be sine of pi over 3 divided by cosine of pi over 3 plus c. Of course, this would be square root of 3 over 2. This would be 1 over 2, and the ratio would cancel out to square root of 3. So we'll get 4 equals square root of 3 here. So this two and this two cancel each other out. So we'll get square root of 3, okay, plus another square root of 3 from here, and plus c. So what do we get? We get 4 equals 2 square root of 3 plus c, which means c is equal to 4 minus 2 square root of 3. We can calculate the decimal value, but we'd rather not, because this is an exact value, and we'd like to keep the exact value. So let's keep c in this form, okay, rather than the decimal form. Okay, so we have then f of t is equal to, well, let me see if I can bring it to the screen so you can, yeah, you can see it now on the screen. So it's all of this plus, now we know what that c is, right? So 2 sine of t plus tangent of t plus that whole constant, 4 minus 2 square root of 3, all right? Like that. All right. So let's do another example. Notice the transition, right? We started with the c unknown, and now we are finding value of c given some additional information, right? So just remember the transition. Okay, so this example, we have the f double prime, or the second derivative, given to us as 2 times e to the t plus 3 times sine of t, and the additional information they have for us is the antiderivative at 0 is equal to 0, and the antiderivative at pi is equal to 0 as well. Okay? All right, so let's find the next antiderivative of, which would be f prime, right? So as we have the solution like that. So f prime t is equal to 2e to the t, and of course cosine would have would be the antiderivative of sine of t, but so the initial function, or the f prime, must have been minus 3 cosine of t, because after that you take the antiderivative of this, you get minus sine of t, which multiplies itself by this and gives us plus 3 sine of t. And of course, let me add the constant. Let's call it c1, because there will be more as we find the next antiderivative, which is the original function. We'll have another variable here, or we can just call it c or d, or c1, c2. It makes no difference as long as we account for it. Okay, since I call this c1, I'm going to call the next one c2. So ft would be, again, 2e to the t, and antiderivative of this would be sine of t. So minus 3 sine of t plus c1x plus c2, right? Okay, so now we can use this additional information to find c1 and c2. So let's do that. So this original function at 0 is 0, so f at 0 is 2 times e to the 0 power minus 3 times sine of 0 plus c1 times 0, right, plus c2. So we already know that that piece is 0. F of 0 is 0, so this, let me move this up a little bit. So this is 0 equals, then e to the 0 is 1, 1 times 2 is 2, minus 3 times that is 0, so minus 0 plus c2. So c2 is equal to minus 2. Minus 2, right? So we have c2. Let's find c1. And of course we have additional piece of information. F at pi is equal to 0, right? So f at pi, we have, this is f right here. So 2e to pi minus 3 times sine of pi plus c1 times pi plus c2. Okay, so we know that f pi is 0. Let me bring it down right there. That's the additional information we were given. Equals e to the pi. Then let's keep it like that. It's just a constant. E to the pi times 2. We're going to keep it this. And this sine of pi, we know it's equal to 0. So it'll multiply by this. They drop out. Then we have c1 pi plus c1 pi. C1 we're looking for, right? C2, we already know what it is. It's minus 2. So plus minus 2, which is minus 2. Okay, so let's manipulate this equation algebraically. What do we get? We get C1 equals minus 2. So let me write it down. So minus, I guess we can do it either way. So 2 minus, I just put this in the middle, so the minus is in the middle. So to move these two terms to the left, divide them by pi, that's all. So 2 minus 2e to the pi divided by pi. Okay, that's C1. So now we have C1 and C2. Therefore, we can write this original antiderivative with C1 and C2 included. So let me do that. Okay, good. You can see both of them on the screen now. So I can now bring this down and rewrite it. So we have f of t equals 2e to the t minus 3 times sine of t plus all of that times x, right? Sine times t, sorry. Sorry, let me fix this, guys. I wrote x here. That should be t because the variable here is t. I'm sure if there was a class as I did this, one of you would correct me. But since you're not here, I catch it later, or I might not even catch it. But that should be the same variable we've been using. Okay, so now that, let me bring it so you can see everything on the screen. So plus all of that, 2 minus 2 times e to the pi over pi times t plus C2, which is minus 2. And again, I promise you that I will clean this before I post it in Canvas. So in Canvas, you shouldn't see these. It'll be cleaned up, but that's what it is. That should be a minus. Okay, like that. All right, so let's do another example here. So we want to find a function f. Of course, this will be the antiderivative such that f prime x is equal to x cubed and the line x plus y equals 0 is tangent to the graph of f. Okay. So the first thing is let's find the antiderivative for this, which would be an easy one. F of x will be 1/4 x to the 4th plus c, right? So then, given this, and this line is tangent to the graph of, not this, but that, right? So we know that this line is a tangent to that graph, in addition to the fact that this is also the equation of the tangent line to the curve f at every point, right? This would be tangent to that at every point. The slope of the tangent function at every point to that function, right? So this would be the slope of the tangent line. So at one point, this line and this curve must have some commonality because this line is also tangent. So let's see. So because y equals minus x, and I'm talking about this. See, so this means that we have that y equals minus x, right? That's this linear function with slope -1, right? And they're telling us that this line with that slope is tangent to the graph of f. Okay, that's significant, good piece of information, because from that, from this information, we know that the slope of this line is -1. So let's call it m is -1, right? But the slope of that line, and we are told that this is the derivative of that antiderivative. So this function calculates the slope of the tangent line at every point to that curve. At some point, it should be equal to -1, right? At some point, this equation should be -1. So let's find out what point that is. So that's the point where this line is also tangent to the curve, to that curve. Okay, so this is different than that, but at one point on that curve, they have equal value. So we can use that information for us to find the antiderivative. Okay, so x cubed then, so therefore, and because, let me actually put braces here. So because f prime x is equal to x cubed, which is here, then we can, from here, we can say that x cubed equal to -1 at one point. At some point, this tangent line and that equation meet at some point on this curve. Okay, we know that. Okay, so let's solve for x using this equation. So therefore, we have x equaling, take the third root of both sides, we get x equals -1. All right? So if, going back to that equation, since x equals -1 now, we know that. So what would y be? Y would have to be 1, right? So -1 plus 1 gives us 0. So let's then, knowing x plus y equals 0, therefore y should be equal to 1. So use that and this to write the point at which -1 comma, this is the point that is shared by the tangent line and this equation, and it's on the curve. Okay, let me write that actually. So that point this point is shared by f prime x equals x cubed and x plus y equals 0. All these three, the antiderivative, the first derivative, and the tangent line share that point. Okay? So why is that so useful? Because now we can use that point to find that constant value c, right? So let's use that. So we have, and I'll just, so from here then, then we have f of x we obtained is equal to 1/4 times x to the 4th plus c, didn't we? So now we know that that point is on this curve, in this function. So then 1 equals 1/4 times -1 to the 4th plus c, we can find c. So let's do that. So 1 equals 1/4 times -1 to the 4th plus c. And from that, c is equal to 3/4. Just manipulate this algebraically and you get that. And 1 minus 1/4, which would be 3/4. Okay, so then the original function, or the antiderivative, must have been f of x equals 1/4 x to the 4th plus 3/4. Like that. Okay. All right, so let's do one more example. I keep forgetting to bring my white out so I can correct those marks right away as soon as they happen. And I'm talking about things like this, things like this. If I had my white out, I could easily just take out and correct that right here in the video, but I have to wait until I get home and to do that. Okay. All right, so here we have an example. So we know that, so if you've taken your freshman physics classes, so you're already familiar with the with the Newtonian physics. So we know that so these are functions of time, right? Acceleration as a function of time, velocity as a function of time, and so on. Like that. Okay? So they're related in that way. As a matter of fact, let me write them like this. So v prime t, or the derivative of the velocity function, is equal to the acceleration function. And the derivative of the distance function is equal to the velocity function. Okay. Okay, so knowing that, suppose suppose a car is traveling 50 miles per hour. So this is feet per second squared. Notice the change, actually I should have, let me underline that. Notice here we have two units, miles per hour and feet per second squared. So everything should be either in miles per something or feet per something, right? We can't have miles and feet mixed. So at some point, we'll have to make these units relatable or the same, based on feet or miles or something like that, or seconds or hours. We should bring all those units to the same platform. Okay. Okay, so here's the information, and we want to find the distance traveled before the car comes to a stop. So there are some very useful information provided to us, producing when the brakes are applied, they produce a constant deceleration. The deceleration is constant of 22 feet per second squared, and because it's a deceleration and not an acceleration, we show that with a minus 22, okay? Acceleration, just like velocity, is a vector, and so it has some direction. So we use minus to indicate the deceleration part. Okay, so if we can then put these in some kind of organized way, let's convert this deceleration to an equation. Then we know that this is solution. So I strongly suggest that you pause, and I know I've been forgetting to remind you of that, but I hope by now, I'm sure you know that I want you guys to pause and do your own work before you see my solutions. Hopefully, if that way, if I have an error in these notes, then you can catch it and report it to me, and I'll be happy to fix it. So that's another side benefit of you doing your own work and comparing it with my solutions here. Okay, so I'm assuming you've done your work and now you're back. And so for acceleration then, let's call it A acceleration as a function of time. We have a constant acceleration of minus 22. Okay? So we have been told that from the beginning that that acceleration is the derivative of the velocity function, vt. So that means if we find the antiderivative of the acceleration function, we're going to get the function for the velocity. So let's do that. So let's find the antiderivative of this. And because this is equal to the derivative of the velocity function, therefore, Vt would be minus 22t, that's our variable, plus some constant, right? So this is the constant in this case. Take a look at the context. In this context, c must have been the initial velocity before the brakes were applied, right? So let's call it initial velocity. V naught being the initial velocity, right? So that. Then we were told that, let's see, so were we given that? So we were given something for initial velocity. Oh yeah, we have that. Great. So we can calculate this easily, but we do have to do, so suppose a car is traveling at 50 miles per hour. So we need to convert that. This is our V naught, This is our V naught, okay? But we need to convert it to, because this was, remember, this was feet per second squared. So I don't want to plug in 50 here because it would be miles per hour and the units of this would be feet per second squared. It won't match. So we need to convert this velocity to, initial velocity to feet per second. So let's do that. So initial velocity is equal to 50 miles per hour times, we have 5,280 feet per mile. So we have, so let's do that. So we, per 1 mile, right, we have 5,000, so let's see, 5,280 feet. And then how about the hours? So for the hours we have 3,600 seconds, right? 60 times 60, 3,600 seconds per hour and 5,280 feet per mile. Okay, so let's convert this then. Please compare this with your own calculator, but I got 220 divided by 3 feet per second, that quantity feet per second as the initial velocity. And I'm keeping it in this form because it's in exact form, rather than converting this to decimal form, which would not be exact. So let's keep it like that. So that's the initial velocity. We can plug that in here and get a full function for the velocity function. Therefore, thus we have the velocity function is equal to minus 22t, right, from here, plus the initial velocity, which we now know what it is, in the same units as this t, or this unit, this minus 22. So 220 divided by 3. Okay, feet per second, and this minus 22 units is feet per second squared. So now it makes sense. Okay, so that being the velocity function, they want us to find the distance function, right? What is the distance traveled? To find that, we need to first find the distance function, right? So, and the distance function, and I need to go to another page here, would be the antiderivative of the velocity function, right? So let's here, so the distance function, I'm assuming you have not taken freshman physics, so you might have already taken it, I don't know. But the distance function is the antiderivative of the velocity function. Okay, thus, so we need to find the antiderivative of that. Let's call it dt, and so that would be minus 22 t squared divided by 2, and plus 223 over 3 times t, right, like that. So of course we can simplify that. Let's do that. And we get the distance function equals minus 11 t squared plus 220 over 3 that times t. And then so this is the, if this is the distance function, then they want us to know how far this car traveled before coming to a full stop, right? So I need to then, so this is our, let me find, so I should have actually, let me bring this back. We have this velocity function, right? So at the full stop position for this car, the velocity is equal to 0. So if I set this velocity function equal to 0 and solve for t, I'll know how long it took for this car to come to a stop, and I can use this time here in the distance function to calculate how far the car traveled before coming to a full stop. So let's do that. Actually, let me add it here. There's enough space here, so I'll add it here. So at full stop position, the velocity is equal to 0, right? Thus, so 0 equals minus 22t plus 220 divided by 3. So solve this for t, and you should get t equals, what did I get? I got 10 over 3. Please verify this with your own calculations. So that's the time it took for the car to come in seconds. So this is seconds. It took for the car to come to a full stop. Okay? So now that we know that, we can easily calculate the distance traveled for the car to come to a full stop. So d at 10 over the distance function when t is 10 over 3 seconds, so 3.33 seconds, right, roughly. So less than 4 seconds, minus 11 times 10 over 3 squared plus 220 over 3 times 10 over 3. And then if you do all this calculation, then you should get, and I finally converted everything to decimal form, you should get roughly 122.2 feet. And let me put so approximately. It took approximately 120 for the car to travel 122.2 feet before it came to a full stop. Okay. So this was basically a capture of, or the first introduction to the topic of antiderivatives. In this course, in the remainder of this semester, we will do a little more with this. We have a few sections in Chapter 5 to go over this topic, but we will expand on that in a major way in Calculus 2. I want to thank you for watching this video until this point, and for now, have a nice day, and I'll see you again next time.